In this video, I'll be solving several rotational motion example problems. So for our first problem, we have find the angle in both radians and degrees subtended by an arc 2.75 meters in length. The arc lies on part of a circle that has a radius of 2 meters. So to start, I'll write my arc length, S, equals 2.75 meters. My radius, R, is 2.0 meters. And theta in radians is defined as the ratio of the arc length to the radius. So if we plug this in, 2.75 meters over 2 meters, we get 1.375 meters, or 1.375 radians. And you should notice this is a dimensionless unit. So radians isn't actually a real unit, it's just a ratio of the arc length to the radius. And so when we do this, we'll always get an answer in radians. And if we want to convert this into degrees, then we know there are 2 pi radians in a full revolution, and there are also 360 degrees in a full revolution. So if we multiply by 360 over 2 pi, we get 78.8 degrees. In the next problem, we're asked to find the period and angular speed for a disk that has a diameter of 315 centimeters and completes 3 revolutions every 2.1 seconds. So first, I will draw a circle, and this circle has a diameter of 3.15 meters. So that means my radius is half of that, or 1.575 meters. And then the definition of a period of a revolution is the amount of time it takes per cycle or per revolution. So cycle or revolution. So the period, we have T equals 2.1 seconds for every 3 revolutions. And so this is our rate. And if we multiply this by 1 revolution, then we get 0.7 seconds. Now we can use our definition of speed, which is just distance over time. And for a complete circle, the distance is just the circumference, or 2 pi times the radius, over the period. But we also know that we have a relationship between the linear velocity and the angular velocity, v equals r omega. So if this is velocity and this is velocity, we can set them equal to each other, and we get r omega equals 2 pi r over t. We have an r on both sides that's going to cancel, and we find that omega is just 2 pi over the period. And so if we plug that in, 2 pi over 0.7 seconds, we will get 9 radians per second. In the next problem, we have a ceiling fan with an angular speed of 150 radians per second, is turned off and slows at a constant rate of 2 radians per second squared. Find the number of revolutions the ceiling fan will make before it stops. Okay, so this looks kind of like kinematics, just for angular quantities. So we're going to start off with an angular speed of 150 radians per second. Our angular acceleration, alpha, will be 2 radians per second squared. And I'm actually going to make this negative since it's going to slow down. And then my final omega will be 0 radians per second, since it's going to eventually come to a stop. And then I'm going to point this out. This is constant, a constant angular acceleration, which when our angular acceleration is constant, that means we get to use our kinematic equations. So notice we don't have any time here, and we're looking for the number of revolutions. So we're looking for delta theta. So the only kinematic equation we have that will work will be omega squared equals omega naught squared plus 2 alpha times delta theta. And then theta, or omega, is just 0. So if we solve for delta theta, we will get minus omega naught squared over 2 times alpha. And if we plug in, we get minus 150 radians per second squared over 2 times a minus 2 radians per second squared. And this will give us 72 radians. Now we just need to convert this to revolutions. 72 radians, we have 2 pi radians for every 1 revolution. And if we plug that in, we get 11.5 revolutions. The next problem, we have a wheel reaches an angular speed of 220 radians per second in 7.5 seconds after accelerating from rest at a constant rate. Find the angular acceleration and the distance traveled by a particle on the edge of the wheel if the wheel has a radius of 0.3 meters. So I'm going to write what I know. Omega is 220 radians per second. Okay, so this is the speed it reaches after some time, so it's final omega. My time is 7.5 seconds. My radius is 0.30 meters. And my initial omega, or initial angular speed, is 0. So I'll use my kinematic equations. So I can solve for angular acceleration using this equation, since I have omega, omega naught, and time. So this goes to 0. And solving for alpha, I get omega over t, or 220 radians per second over 7.5 seconds. And this is 29.3 radians per second squared. Now to find the distance traveled, we'll use the fact that s is equal to r theta. So if we're moving through some displacement, our r is going to remain constant, but our theta will change. So we need to find delta theta in order to find delta s, or our linear distance traveled around this arc. So to do that, we'll use another kinematic equation. And since now we have angular acceleration, we can use this kinematic equation. Omega naught is just equal to 0. So delta theta is 1/2 our angular acceleration, 29.3 radians per second squared, times time, 7.5 seconds, all squared. And that gives us 824 radians. And then if we plug this into our equation above, we have the radius, 0.30 meters, times 824 radians. And that gives us 247 meters. The next problem we have, it takes 16 seconds to make a complete revolution on a merry-go-round if you're at the edge 2.5 meters from the center. Find your tangential speed if you're standing at the edge. So if we draw a little circle representing our merry-go-round from the top, this merry-go-round has a radius. In this case, it's 2.5 meters to the edge. And we want to find our tangential velocity, so v tangent. And we know that our period is 16 seconds, and our radius is 2.5 meters. So we can again use our definition for speed, which is just distance over time. And this, for a complete circle, is just the circumference over the period. And since we have the radius and the period, we can just plug in 2 pi times 2.5 meters all over 16 seconds. And that gives us 0.98 meters per second. Next problem, a basketball can be modeled as a thin spherical shell. If a basketball has a mass of 600 grams and a radius of 24 centimeters, find its moment of inertia and kinetic energy if it rotates on a player's finger at 5 revolutions per second. So we'll start by drawing a rough basketball, and it is going to rotate. And so we have our mass as 0.600 kilograms. The radius is 0.24 meters. And our omega is in revolutions per second. So 5 revolutions per second. So we'll want to convert that to radians. This is 1 revolution equal to 2 pi radians. And that gives us 10 pi. I'll just leave this pi in here. Radians per second. That way we don't get a long decimal. And then I know in order to get the kinetic energy of rotation, that's going to be 1/2 I omega squared. So I have omega. Now I need to find I first. So the moment of inertia for a thin spherical shell will be 2/3 mr squared. So this is something you would look up in a table or in a textbook. And then we can plug in, so 2/3 0.600 kilograms times 0.24 meters squared. This gives us a moment of inertia of 0.023 kilogram meter squared. And now I have omega, so I can plug into my kinetic energy. So 1/2 0.023 kilogram meter squared times omega squared, which is 10 pi radians per second, that all squared. If we plug that in, we get 114 joules. The next problem, we have a solid ball with a mass of 2.5 kilograms and a radius of 0.15 meters is rotating at 100 radians per second. Find the kinetic energy of the solid ball, then find the height from which you would need to drop the ball so that it would have the same kinetic energy when it reached the ground. So I'll start by just drawing again, just to get an idea of what's going on. My ball that's spinning, and it has a mass of 2.5 kilograms, a radius of 0.15 meters, and an angular velocity of 100 radians per second. Now I know to find the kinetic energy, it will be 1/2 I omega squared, so I need to find I. So I for a solid ball will be 2/5 mr squared. So this will be 2/5 times 2.5 kilograms times 0.15 meters, all squared. And this gives me 0.0225 kilogram meter squared. So now I can plug in, and I have 1/2 my moment of inertia, 0.0225 kilogram meter squared, times omega, 100 radians per second. That's squared. And this gives me 112.5 joules. So now if we want to find the height that we would need to drop this from, then we use conservation of energy. So our initial energy would equal our final energy. Well, initially we would only have potential energy, so UI, and we would be dropping it from rest, and then at the end when it would hit the ground it would only have kinetic energy. So this would give us mgh equal to our final kinetic energy that we just found. And so we can solve for the height just by taking k and dividing by mg. So this would be 112.5 joules divided by 2.5 kilograms times 9.8 meters per second squared. That should be a 5. And this gives 4.6 meters. Next problem, we have a solid disk with a radius of 0.45 meters is translating at 4 meters per second while spinning at 200 RPM. Find the height reached by the disk if it encounters a hill and begins to roll up. So here we have a solid disk that is rolling and then it encounters a hill. It is both translating with some velocity v and rotating with some angular velocity omega. And so it has a radius of 0.45 meters, a linear velocity of 4 meters per second, and an angular velocity of 200 RPM, or revolutions per minute. So we'll want to convert that. So this is 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So this will give us 21 radians per second. And now we can use conservation of energy. So at the end, when it goes up the hill, it will have the same energy as it started with. So we have final kinetic plus final potential is equal to initial kinetic plus initial potential. In the beginning, there's not going to be any potential energy because it's going to be at what we call y equals 0. And at the end, it's eventually going to stop rolling up the hill when it gets to its max height. So its kinetic energy will be 0. And so we'll have the final kinetic energy, mgh, where h is just the height that it reaches. And that's going to equal the total kinetic energy it has initially, which is going to be partially translational kinetic energy, 1/2 mv squared, but it's also rotating, so it has 1/2 I omega squared. So now I need to find omega. So this is a solid disk, so I would look that up, and it would have a moment of inertia of mr squared. And then we can use the fact that v is equal to r omega, so omega is equal to v over r, and we can substitute. So now we get mgh is equal to 1/2 mv squared plus 1/2. We'll substitute in for our moment of inertia and get mr squared, and then again for our omega and get v squared over r squared. Now we can cancel some things out, so we have mass in every term. And then on this last term, we also have an r squared that cancels this r squared. So we're left with gh equals v squared over 2 plus v squared over 2, which is just v squared. And we can solve for the height, which is just v squared over g, or it is going 4 meters per second squared over 9.8 meters per second squared. And that will equal 1.63 meters. So it turns out we didn't even need r omega. In the last problem, we have a solid sphere with a radius of 0.25 meters that is at rest at the top of a ramp 1.5 meters above the ground. Find the speed of the sphere at the bottom of the ramp if it rolls without slipping, and again if it rolls, if the ramp is smooth and it slides down. So we have a sphere that's rolling down. So at first it is at rest, so it's not translating or rotating. And then it's going to get to the bottom, and it is both rotating and translating. And we're looking for the final speed. So I'm going to do it while it's sliding first, since that's the simpler case. So in this case, or in both cases, we're going to use conservation of energy. But in this case, it'll be a little bit easier, since it only has one type of kinetic energy. So initially, just write initial kinetic plus initial potential is equal to final kinetic plus final potential. And so initially it's not going to be moving, so it has 0 kinetic energy. And at the end it's going to reach the bottom and have no potential energy. Okay, so we'll call the ground y equals 0, where it has no potential energy. And so we get mgh for its initial potential energy. And if it's just sliding, it only has translational kinetic energy, 1/2 mv squared. So our masses will cancel, and we will get the velocity is equal to the square root of 2gh, or square root of 2 times 9.8 meters per second squared times 1.5 meters. and that's going to equal 5.4 meters per second. Okay, so that's our first velocity. So now let's look at the case where it is rolling without slipping. So in this case, we still want to use conservation of energy. Okay, so we end with what we start with, and we start with initial kinetic energy, initial potential energy, final kinetic plus final potential. So again, we have 0 kinetic energy to start with, 0 potential energy at the end. Our initial potential energy will still be mgh, but now we have both forms of kinetic energy, both translational 1/2 mv squared and rotational 1/2 I omega squared. Okay, so we first need to identify our moment of inertia. So I'm going to write this over here. Our moment of inertia for a solid sphere will be 2/5 mr squared. So that's 5. And then we're also going to use the fact that omega is v over r, like we've done in previous problems, and we're going to substitute. So we get mgh equals 1/2 mv squared plus 1/2 times 2/5 mr squared. And then our omega squared would be v squared over r squared. So we have a lot of canceling out we can do. First thing is we have a mass in every term, so that goes away. In this last term, we have these 2's that are going to cancel each other, and we also have these r squareds that go away. So if we rewrite this and clean it up, we have gh equals v squared over 2 plus v squared over 5. And so we can get a common denominator and get 5v squared over 10 plus 2v squared over 10, which is just going to be 7v squared over 10. So gh equals 7v squared over 10. And this will give us v equals square root of multiply by 10, divide by 7, take the square root. And if we plug that in, so 10 times 9.8 meters per second squared times 1.5 meters per second, or 1.5 meters, all over 7, we get 4.6 meters per second. Okay, so you're translating a little bit slower than you were in this case, and that's because some of your initial potential energy went into rotating the sphere, so it went into rotational motion, and so your translational motion isn't quite as fast. So I hope this helped you get a grip on some rotational motion concepts and how you solve some example problems, and I'll see you in the next video.